Right now, inside your engine block, beneath the oil and past the pistons, there's a slow, invisible robbery happening. Every single time you turn the key, 30% of the power your engine was born with is slowly being destroyed by friction. In 2023, the global automotive repair industry generated $880 billion. A massive chunk of that empire is built on rebuilding engines that should never have worn out and charging you thousands of dollars for work that could have been delayed for decades. They built this system to keep you in the dark, but Japanese fleet mechanics have been quietly using a compound that costs less than a bottle of water, just $2, to force their engines to run for 500,000 miles without a single rebuild. Today, I'm going to show you exactly what this raw mineral is, the classified military tests the industry tried to bury, and the 15-minute driveway protocol that will make your engine practically immortal. Now here's where most people get misled, because you've been trained to believe that modern synthetic oil is the ultimate solution. You've seen the ads. Advanced protection, maximum performance, engineered at the molecular level. And technically, none of that is false. Synthetic oils are better than older formulations. They handle heat better. They flow faster. They resist breakdown longer. But there's one brutal truth they never emphasize. Even the most expensive oil on the planet fails at the exact moment your engine needs it most. Inside your engine, components are moving at insane speeds. 3,000, 4,000, sometimes even higher RPM. Pistons firing, camshafts spinning, metal surfaces sliding against each other thousands of times per minute. Under these conditions, oil is supposed to create a protective film that keeps those surfaces separated. And most of the time, it does. But not all the time. Because there is a specific moment, an unavoidable moment, where that protection collapses. It's called boundary lubrication. This is the boundary zone, and it happens during cold starts, sudden acceleration, or heavy load conditions. In this zone, pressure becomes so intense that the oil film compresses to the point where it can no longer fully separate the metal surfaces. The protective layer becomes microscopically thin, too thin to prevent contact. And when that happens, it's no longer lubrication. It's collision, bare metal against bare metal, microscopic tearing, surface degradation, permanent damage. This is not a rare event. It happens every single time you start your engine, every commute, every short trip. And here's the part most people never hear. This boundary zone is where up to 90% of all permanent engine wear occurs. Every scratch on your cylinder walls, every tiny imperfection that slowly reduces compression and efficiency. It all happens here, where oil alone fails. So now you have to ask yourself something uncomfortable. If the industry knows this, and they do, why is oil still the primary solution being sold to you? Why are you told to spend more money on better oil when the fundamental problem isn't being solved at all? Because oil was never designed to handle this phase. It was designed to reduce friction when a full film exists, not when that film collapses. That gap, the boundary zone, is where the real damage happens, and it's also where the real solution lives. This is where everything changes, because decades ago, engineers identified a material that doesn't behave like oil at all. It doesn't rely on fluid thickness. It doesn't get squeezed out under pressure. Instead, it operates exactly where oil fails. That material is called molybdenum disulfide, MOS2. And unlike the synthetic formulas pushed by major brands, this isn't something created in a lab to maximize profit margins. It's a naturally occurring mineral mined directly from the earth. A raw black powder with a crystalline structure that allows its layers to slide over each other with almost no resistance. But more importantly, under heat and pressure, it doesn't just sit between surfaces. It bonds to them. It embeds itself into the microscopic imperfections of metal, creating a permanent, ultra-low friction barrier right inside the boundary zone. And that changes everything. Because now, instead of relying on a temporary oil film that disappears under pressure, you have a solid layer that remains in place, protecting your engine at the exact moment it is most vulnerable. This is not about improving oil. It's about replacing its weakest point. And because MOS2 is a natural mineral, it cannot be patented. No single company can control it. No corporation can monopolize it. Which means it never became the centerpiece of a billion-dollar marketing campaign. Now step out of the marketing world for a second and into real history. Because what you're about to see isn't a theory, and it's not something invented for clicks. It's a timeline of evidence that stretches back over 200 years, long before synthetic oil existed, long before modern automotive companies had anything to sell you. In the 1780s, deep inside the mines of Sweden and Norway, workers faced a brutal mechanical problem. Massive ore carts, loaded with tons of material, were grinding their iron axles into failure. Traditional lubricants, animal fats, and early oils simply couldn't handle the pressure. They broke down. They burned off. They failed. So miners turned to something else, a strange dark mineral they crushed into powder and applied directly to the metal. They called it black grease. What they discovered was extraordinary. Instead of disappearing under load, this material left behind a hard, slick film on the iron itself, a coating that didn't wash away, a layer that continued to reduce friction even after the visible material was gone. They didn't understand the chemistry, but they understood the result. Their equipment lasted longer. It moved smoother. It failed less. Fast forward to the 1840s. Europe, military expansion, harsh winters, and a very different problem. Rifles freezing solid in sub-zero conditions. Prussian gunsmiths needed a way to keep rifle bolts moving under extreme cold. Conditions where oil thickened and failed completely. They turned, again, to the same black mineral. Applied to the bolt mechanisms, it did what oil could not. It maintained smooth operation even in freezing temperatures. No seizing, no lockup. Just consistent mechanical movement where traditional lubrication completely broke down. Once again, no branding, no industry. Just performance solving a problem oil couldn't. Then everything changed in 1941. World War II forced engineering to evolve faster than ever before. Machines were pushed beyond limits. Tanks in desert heat, aircraft in freezing altitudes, engines running under constant stress. The United States military began conducting intensive classified lubrication testing at the Aberdeen Proving Ground. Their goal was simple: find something that could survive extreme pressure and temperature without failing. They tested standard military greases, they tested petroleum-based oils, and then they tested molybdenum disulfide, MOS2. The results were impossible to ignore. Under extreme conditions, MOS2 reduced metal fatigue by up to 80% compared to standard lubricants. Sherman tank engines operating in the Sahara showed dramatically lower wear. B-17 bomber components exposed to high-altitude freezing conditions maintained smoother operation with significantly less degradation. This wasn't a minor improvement. It was a complete shift in how friction could be controlled under stress. The material didn't get squeezed out like oil. It didn't evaporate under heat. It bonded to the metal, creating a protective layer exactly where traditional lubrication failed. And because of its strategic value, much of this research remained classified or buried in technical archives after the war. Now move forward again. 1964, Tokyo, the Olympics, millions of visitors, and a massive logistical challenge. Taxi fleets running non-stop in brutal stop-and-go traffic. Engines were wearing out faster than expected, especially under constant start-stop conditions, the exact environment where boundary lubrication causes the most damage. The Japan Automobile Research Institute, known as JERI, launched a 6-year study to solve this. They tested 47 different additives and lubrication strategies, looking for something that could protect engines under real-world stress. The result was clear. Molybdenum disulfide reduced metal-on-metal friction by approximately 73%. Not in theory, not in lab-only conditions, in real operational testing. By 1971, major manufacturers, Toyota, Honda, Nissan, Mazda, began quietly integrating MOS2-based solutions into their engineering processes, particularly in high-stress components. Not advertised, not marketed, but used where longevity mattered. And this is one of the hidden reasons Japanese domestic vehicles developed a global reputation for durability. It wasn't just design, it wasn't just manufacturing quality, it was a deeper understanding of friction and how to control it at the microscopic level. So now you're looking at over 2 centuries of consistent, independent validation. Mining, military, industrial engineering, automotive research, all pointing to the same conclusion. This material works where oil fails, which brings us to the uncomfortable part. If this has been known for so long, why isn't your mechanic offering it? Why isn't it standard practice? The answer takes you straight into the business side of the industry. After World War II, companies like DuPont and Dow Chemical had already invested billions into petroleum-based lubrication systems, refineries, distribution networks, product lines, entire economies built around oil-based solutions that needed to be replaced regularly. That's the key: regular replacement, continuous consumption, recurring revenue. Now introduce a problem, a naturally occurring mineral that costs almost nothing, cannot be patented, and dramatically reduces wear over long periods. That's not a product, it's a disruption. Because you can't control it, you can't lock it behind branding, and you definitely can't build a billion-dollar recurring business around something people use once every tens of thousands of miles. So instead of eliminating it, the industry reshaped it. Today, if you walk into a store, you'll still find products labeled with MOS2, but look closer. These are not raw solutions. They are diluted formulas, typically around 2% concentration, mixed into petroleum carrier oils, a tiny fraction of the active material surrounded by filler, then packaged, branded, and sold to you for $18 or $25, sometimes $35. What originally cost $2 is now stretched, diluted, and repackaged into something that looks advanced, but never delivers the full effect. Because if it did, it would reduce the need for repairs, replacements, and repeat purchases. And that's the system. Not a conspiracy built on secrets, but a structure built on incentives, a system where the most effective solution isn't the most profitable one, so it gets buried, diluted, and quietly pushed to the edges. But here's where everything changes again, because history is one thing, laboratory data is another, but nothing is more powerful than real-world proof. Vehicles, engines, fleets operating under pressure, showing exactly what happens when this material is used the way it was originally intended. And that's exactly what we're about to look at next. Now this is the point where everything either becomes real or falls apart. Because if you truly understand the science behind this, you stop seeing it as a trick and start seeing it as engineering logic. And once that clicks, you'll never look at engine wear the same way again. Let's break it down in the simplest, most powerful way possible. Molybdenum disulfide, MoS2, is what scientists classify as a transition metal dichalcogenide. That sounds complex, but the structure is what matters. Imagine an ultra-thin sandwich made of atoms. One layer of molybdenum atoms sits in the center, and on both sides of it are layers of sulfur atoms. Now stack thousands of these sheets on top of each other. What you get is a crystalline structure made of perfectly flat hexagonal layers. Here's the key. The bonds within each layer are extremely strong, but the forces between the layers, called van der Waals forces, are incredibly weak. That means these layers can slide over each other with almost zero resistance. Under a microscope, it behaves like sheets of wet glass gliding across one another. This is why MoS2 is one of the most effective solid lubricants ever discovered. Now compare that to oil. Oil is a liquid. It works by creating a temporary film between surfaces. But under extreme pressure, like inside your engine, that film gets squeezed thinner and thinner until it can't fully separate the metal anymore. That's the boundary zone. That's where damage happens. But MoS2 doesn't rely on staying between surfaces as a fluid. It becomes part of the surface itself. This is where the real magic, actually the real chemistry, happens. MoS2 particles carry a natural affinity toward metal, especially iron and steel. When you introduce them into a running engine, they don't just float around randomly. They are electrostatically attracted to the metal surfaces. And under heat and pressure, the exact conditions inside your engine, they undergo what's called a tribochemical reaction. That means the particles don't just sit there, they bond. They embed themselves into microscopic imperfections, scratches, and pores in the metal. Over time, they form a thin, uniform crystalline layer that becomes part of the surface itself. Think about what that means. You're no longer relying on oil to protect bare metal. The metal is no longer bare. And here's where it gets even more powerful. This bonded layer is incredibly stable. It doesn't wash away with oil changes, it doesn't break down under normal engine temperatures, and because of its layered structure, it continues to provide ultra-low friction even under extreme pressure. In many cases, this layer is effectively harder and more wear-resistant than the original surface it's protecting. You're not just reducing friction, you're repairing and upgrading the surface at a microscopic level. Now let's talk numbers, because this is where the argument becomes undeniable. Standard synthetic motor oil, even high-end formulations, typically operate with a friction coefficient between 0.08 and 0.12 under boundary conditions. That's just the limitation of liquid lubrication, but when MoS2 is properly applied and bonded, that number drops dramatically to around 0.03 to 0.05. That's a 60 to 70% reduction in friction at the exact moment your engine experiences the most damage. Not during ideal conditions, not during steady cruising, but during cold starts, acceleration, and load, where engines actually wear out. And this isn't theoretical. A 2018 study published in Tribology International Tested Engines treated with MoS2 under controlled conditions. After 200 hours of operation, the results showed up to 68% less cylinder wall wear compared to engines using conventional lubrication alone. Less wear means tighter tolerances, better compression, more efficient combustion, and dramatically extended engine life. Now let's take this out of the labs and into the real world, because this is where it becomes impossible to ignore. In 2009, a private airport transfer fleet manager in Osaka decided to test this for himself. No sponsorship, no marketing, just practical engineering thinking. He applied raw MoS2 powder to a fleet of 22 Toyota Corollas, vehicles that run constantly under heavy stop-and-go conditions, the worst-case scenario for engine wear. Over time, the results became clear. His oldest vehicle, a 2004 Corolla, surpassed 580,000 kilometers on the original engine block. No rebuild, no catastrophic failure, still operating. Multiple vehicles in the fleet crossed 400,000 kilometers with similar performance. Compression remained stable, oil consumption stayed low, wear rates dropped far below industry norms. But the real difference wasn't just lifespan, it was cost. His average engine-related maintenance cost. Now we get to the part where everything becomes real, the exact protocol. Because if you get even one step wrong, you don't get the full effect. And if you follow it correctly, you fundamentally change how your engine wears for the next 50,000 to 70,000 miles. This is not something you rush. This is something you execute precisely. First, sourcing the material. You are looking specifically for technical grade molybdenum disulfide powder, not a branded additive, not a liquid treatment, pure powder. And this detail is critical. The particle size must be clearly labeled as under 2 microns. If it's not, do not use it. Larger particles won't properly embed into the metal surface and will simply circulate without bonding. This one detail determines whether the entire process works or fails. A 100-gram bag typically costs between $2 and $4, and that single bag is enough for 5 to 7 full treatments depending on your engine size. That's years of protection from something most people spend more than that on a single coffee. Now, step 1, the warm-up. Never apply this to a cold engine, ever. Start your car and let it run for 10 to 15 minutes until it reaches full operating temperature. The oil needs to be fully thinned out, circulating smoothly through every channel, and more importantly, the internal metal surfaces need to be hot. Heat is what allows the tribochemical bonding process to begin immediately. A cold engine delays that reaction and reduces effectiveness. This step is non-negotiable. Step 2, the dosage. Precision matters here. For a standard 4-cylinder engine up to 2.0 liters, you use exactly 5 grams of MOS2 powder. For engines between 2.0L and 3.5L, use 7 grams. And for larger engines, V6 or V8 above 3.5 liters, use 10 grams. Do not guess. Do not overpour. More is not better. The goal is to create a thin, uniform protective layer, not to overload the oil system. Step 3, the mix. This is where most people make mistakes, so pay attention. Do not pour the powder directly into the engine. Instead, take a small, clean cup and add about 30 milliliters of your current engine oil. Then add your measured powder into that oil. Stir it continuously for about 60 seconds. You'll notice something important. It will not dissolve. It will form a dark gray, almost metallic-looking suspension. That is exactly what you want. If it dissolves, something is wrong. If it clumps heavily, it hasn't been mixed enough. You want a smooth, evenly distributed suspension so it can enter the engine uniformly. Step 4, the pour. With the engine still idling, not turned off, remove the oil filler cap. Slowly pour the mixture into the engine. Slowly is critical. You're feeding it into a live circulating system. Pour too fast and you disrupt distribution. Once it's fully added, replace the cap and let the engine continue idling for about 20 minutes. This allows the particles to circulate through the entire system. Camshaft lobes, lifters, bearing journals, and most importantly, the cylinder walls. This is the initial coating phase. Step 5, the burnish phase. This is where the permanent transformation happens. After the idle phase, you drive the car normally for the next 500 to 800 miles. No special driving required, just normal use. During this time, the heat and mechanical pressure inside the engine force the MOS2 particles into the microscopic surface of the metal. The piston rings, moving under high pressure, effectively press the material into the cylinder walls. This process is called burnishing, and once it happens, the layer becomes permanent, not temporary, not dependent on oil. A bonded, ultra-low friction surface that remains even after multiple oil changes. This is why one application can last tens of thousands of miles. Now there's one critical warning you cannot ignore. Never use this in motorcycles or any system with a wet clutch, where the engine oil and clutch share the same fluid. The friction reduction is so effective that it will cause the clutch to slip almost immediately. This protocol is for engines only, where reducing friction is the goal, not systems that rely on friction to operate. Now step back for a second and understand what you've just done. You didn't buy a product, you didn't subscribe to a system. You applied a raw material that changes the physics inside your engine. You've taken control of the single most destructive phase of engine operation and replaced it with a permanent protective layer. That's not maintenance, that's leverage. And here's the reality. Most people won't realize until it's too late. You just saved yourself thousands of dollars in future repairs.